Okay, have you ever worked with shear and moment diagrams before? If you took my wonderful statics class, you certainly have, but this beam is a little bit more complicated than what you would find in statics, in elementary statics. So notice all the loads here, the general reactions. Roller at A, so I've got a vertical reaction. Similarly with C, there's a wall at G, so I've got horizontal vertical reactions as well as a moment reaction. At B and E, you have hinges. So the first thing I should probably do is calculate what the external reactions are. I don't think I can do it based upon the rules of equilibrium, or I should say the equations of equilibrium. There's too many unknowns. So I'm going to dismantle this. I'm going to unbolt it at hinge B, and I'll analyze segment AB first. Okay, before I analyze segment AB, I notice that there are no horizontal reactions to speak of, so I can immediately say that the horizontal reaction at G is 0. So no calculations required for that. Okay, so between A and B, 2 kilonewtons per meter times 3 meters is 6. So when I redraw that, I'll have this. Okay, so 6 kilonewtons, that's the resultant. A sub y and B sub y you can find. You'll find that it's 3 each, and a B sub x is 0, no horizontal reactions. Okay, so B sub y is 3, and A sub y is 3. Okay, how is that? Okay, so now I know what A sub y is. So A sub y, 3 kilonewtons. Okay, so that takes care of that. Now I'm going to analyze segment BE. Okay, so analyze that separately. So I recopy segment BE. Notice all the dimensions here. I recopy that segment here. There's a hinge at E and at B. Typically there would be horizontal reactions as well, but there are no horizontal forces to speak of, therefore I'm not going to bother showing the horizontal reactions that would typically be found at a hinge. Okay, so I've got two unknowns, C sub y and E sub y. I could take the sum of the moments about point C or the sum of the moments about point E to find one of those reactions. So I'll find the sum of the moments about point E, E as in echo. So look here what I did for the sum of the moments about point E. 4, that's this 4, that point moment at point D, 4 minus C sub y times 3. C sub y is right here. The moment arm is 3, plus 3 times 4. That's the B sub y you see at the end. The moment arm is the entire length of the segment. I find that C sub y is 5 1/3 kilonewtons going up. And then once I determine that, well, let me write that on here. Okay, 5 1/3. Once I know that, I can find the sum of the forces in the y direction. 3 going down at point B. 5 1/3 going up at point C, that's what I just determined, plus the reaction at E going up, and I find that E sub y is actually going down, so I could make the arrow point in the other direction, or when I write it I could just put a negative in front of the value. Okay, so negative 2 1/3. Okay, how was that? Okay, so now I'm going to analyze segment EG. Okay, so I'm going to analyze segment EG. Oh, I know now what CY is, don't I? C sub y is 5 1/3. Okay, so I'll write that on here. Five 1/3. Okay, how's that? This drawing is pretty busy. Okay, so now I'll analyze segment EG. So unbolt it at the hinge and draw a separate free body diagram. And now I have segment EG. Okay, now notice the E sub y carries over. Now look what I did here. For the previous segment BE, I got E sub y as negative 2 1/3, but it's negative, so it actually points down. So if it points down, then it's going to have to point up where it meets segment EG, but notice that I dumped the negative sign. I don't like having negative signs in front of the number. I prefer to look at the vector and know which direction it's going in. So I'll pause the video and rewind if you need to reconcile with yourself why I'm showing it the way that I'm showing it. positive 2 1/3 going up. Okay, so what am I trying to find? Oh, and one more thing. Notice I don't show the horizontal reaction at G because there were no horizontal forces to speak of. Okay, so how do I find any of this? I could take the sum of the moments about point G to find M sub G. And I could take the sum of the forces in the y direction to find G sub y. So that's what you'll see appear in just a moment, like magic. And there it is. So the sum of the moments about point G is 0. I find that M sub G, make sure you know where I'm getting these from. M sub G is 1/3 kilonewton per meter. I got a positive value when I solved this equation, meaning that I am showing it the correct direction. So this is 1/3 of 0.3. I'll remember what the units are, kilonewtons times meters. And then the sum of the forces in the y direction is 0. I'm getting 2/3 kilonewtons up. So right here, 2/3 or 0.6 with a repeater bar above the 6. Okay, how's that? Transfer those over to the original, the main figure. Okay, so here's the main figure. So G sub y, 2/3. And then I put a box around it so that if I look at this later on, I'll know that that was not given. I had to derive it. And M sub G, 1/3 kilonewton times meters. Okay. So now I have all the external reactions. Okay, now, did I make any arithmetic errors? I don't know. I'm just one lone guy working in his private studio here, so maybe I made an arithmetic error. How can you verify me? Well, you could check the equilibrium of the whole thing. Pick some point, G would probably be the most convenient. Pick some point and check that it's in equilibrium. The sum of the moments about point G is 0. Check that the sum of the forces in the y direction is 0. Check that this whole thing is in equilibrium. And if it is, then I probably did everything correctly. So I'll leave that up to you. So I check it myself. Be careful here. This is the M sub G is 0.3 with a line above the 3. I think I forgot to put that a moment ago. That's a 1/3, not 3/10. Okay, so did you check this for equilibrium? One more thing I want to mention. When I found the moments about point G, remember this? Be careful, this M sub G is the reaction. This M sub G is the general moment about point G, so I know they look the same, M sub G, M sub G. It's a little bit sloppy on my part. So maybe if I make this capital M by putting a little tail on it. Okay, I don't know if you can see that little tail. Capital M sub G, cursive capital M sub G would mean the general moment about point G. This M sub G is specifically the reaction. Okay, so let me try this again. So here are the final reactions. Okay, now what did the original directions ask for? Shear and moment diagrams? Okay, well, why don't I break this up into segments again? I'm going to analyze segment AB. I'll draw the shear and moment diagrams for that, or at least I'll derive the equations. I'll derive the equations for the shear and the moment, and then I'll put together the diagrams at the very end. So here's segment AB. Okay, so I'm cutting out segment AB. It's between my fingers. I know what the reaction at A is, so I got that here. From my previous analysis, remember this? I know the reaction at B, that's also 3. Okay, now a common mistake is that people try to use the resultant of 6 kilonewtons. Remember that resultant of the distributed load? That does not play a role here in terms of finding a general equation for the shear and moment. So it's very tempting to use that resultant. Don't do it. What I'm going to do here is take cut AA. Okay, so I'm going to cut it. I'm only going to draw the part that's to the left of my thumb. So that'll be the next drawing you see. Cut section AA and analyze to the left of it. Okay, so I cut it at section AA, so I have this. Okay, now where is AA located at? What's the distance here between point A, capital A, and where I make the cut? Well, I don't know, I didn't specify. So I'm going to keep it general. I'm just calling it a general distance X. so that x could vary all the way from 0 until I get to point B, which is 3. Okay, now what happens to that distributed load? It's 2 kilonewtons per meter, so if I cut at a distance x from capital A, that means that the resultant, so now I am interested in the resultant would be 2 kilonewtons per meter times x meters, and that would act in the middle of the cut. So I'm not using a ruler, I'm trying to eyeball this, but this looks like about the center, maybe a little bit over. Okay, so this is the resultant. Okay, you see that? Okay, it's not going to be 6. Unless I'm at point B, that resultant is not going to be 6. It's going to be the 2 kilonewton per meters times the length over which it acts, which is x. So what I'm looking at here is a magnitude of 2x. And that acts at x over 2 from point O where I make the cut, and point A. I forgot to put an A on there. Okay, so it's going to bug me until I do it. So this is point A, and point O is where I make the cut. Okay, so what's this have to do with shear and moment? Well, where I make the cut, there's a certain internal shear, which I'm going to show going down. I'll consider down to be positive for purposes of calculating the internal shear. And there's an internal moment, which I will show as going counterclockwise. And normally there'd be an internal, usually there would be an internal normal force as well, but there were no external axial forces, so that's not going to be an issue. Okay, so I'm using the sign convention that most textbooks use. That is that the internal shear tends to want to rotate the segment clockwise. If you imagine that that V tends to want to make this thing rotate, it tends to want to make it rotate clockwise. And the positive internal moment tends to want to cause this thing to bend concave up. Okay, well, I don't know if you can envision this, but if I had another moment on this side that was going in the clockwise direction, this is going counterclockwise, it would tend to want to make this concave up. So I'll say it again. The sign convention, a positive internal shear tends to want to rotate the segment clockwise, and positive internal moment tends to want to make the beam concave up, the deflected shape concave up. So that's the sign convention I'll follow. Okay, so the equilibrium of this segment, I need the sum of the forces in the y direction and the sum of the moments about point O. So I'm going to derive some equations for those. I'm also going to show the dimension here, x over 2. Okay, so I find the sum of the forces in the y direction for this segment. 3 going up, 2x going down, v going down. So solving that for v, ergo, that means therefore, v is negative 2x plus 3. Call that equation 1. That is for x between 0 and 3. X is measured from point A, so x is between 0 and 3. Okay, how is that? For the internal shear, so what this is an equation for the internal shear at any old location between A and B. And then similarly for moment, sum of the moments about point O is 0, m, internal moment, plus 2x times x over 2, that's this resultant times the moment arm, minus 3x, this 3x times moment arm. I solve this for m, and I get negative x squared plus 3x, a quadratic equation. That's also for x being between 0 and 3. And to be careful, x is measured from A. What happens if you stick 3 in here? X is 3. If I'm standing at point B, that means x is 3 because I'm 3 meters away from point A. X is measured from A. One thing I want to mention here, if you put x is equal to 3 in here, you'd have negative 9 plus 9, which is 0. So what equation 2 is telling me is that the internal moment would be 0 at point B. If I go back to the original structure, the original drawing, that makes sense that B, the moment, should be 0 because a hinge cannot carry moment. Okay, so that seems to make sense. So my arithmetic is probably correct. The hinge can't carry any internal moment, and my equation reflects that. So next I'm going to analyze. Okay, so I'm done finding the internal shear and moment for AB. Now I'm going to analyze BE. Analyze BE. Okay, now here's segment BE. Now, unlike that previous analysis, AB, I can't just get away with one cut here because the shear or the moment equation, or both, will change anytime something new happens. So this time I'm going to measure from point B, so my x value will be based on x being 0. X being 0 at point B, so at point C x would be 1, at point D x would be 2, etc. So since, well, between B and C there's nothing going on really, so I can take one cut between B and C, and then at C we've got a new reaction that's coming in, so that means I have to take another cut to the right of C. But then at D there's something else going on, so I have to take another cut between D and E. So I have to take several cuts here to reflect that we've got different things that occur along the length of this beam. So I'm going to create 3 cuts here. So there you have the 3 cuts, B, little b, C, that's lowercase c. This point would be uppercase C. I guess it's hard to tell the difference. Cut D. So now I'm going to analyze the cut at BB. So I'm going to take this little portion right here between my thumbs, and I'm going to derive shear and moment equations for that segment. I'll call that section BB. So there's the section. Okay, that little section to the left of the dashed line here. The dashed line BB. Okay, so now I'm going to check the equilibrium of this by taking the sum of the forces in the y direction, set that equal to 0. That'll give me the equation for shear. And then the sum of the moments about point O. O is where I made the cut. And that'll give me an equation for the internal moment. And I'm using the usual sign conventions here. And when I do derive those equations, those will be good until I get to point C, at which time I have to derive some new equations. And now applying the equilibrium equations, sum of the forces in the y direction is 0, I get shear is -3 kilonewtons. For x being between 0 and 1, remember that x is measured from point B this time. So I say till C here, because that x is equal to 1. If x is equal to 1, then I'm at point C. Okay, then similarly for the moment, follow my work here, the sum of the moments about point O, and I get an equation for the moment. Again, x is measured from point B in this case. Alright, next cut. See, I've got something new going on at point C. I've got a reaction coming in. So my next analysis will be section CC. So I'm going to analyze to the left of that. See the part to the left of my thumb? I'm going to pull that part out and analyze it. Derive equations for internal shear and internal moment. So x is measured from point B. X is still measured from point B. I make the cut at CC. Here's the original drawing. Okay, so I'm cutting it through here. Okay, there's a 1 meter distance between B and C, as you can see here. Okay, so now I'm going to set up equilibrium equations for this segment. And in doing so, I'm going to find equations for the shear and the moment at point O, where the cut was made. So when I find the sum of the forces in the y direction, I have this equation 3 down. The reaction at C, that's 5 1/3 up, minus the unknown internal reaction at point O. Okay, rewriting this, I find that the internal shear is 2 1/3 kilonewtons. Okay, be careful, I made a typo here, and this is ink, and I'm not going to redo the whole thing. This is x is between 1 and 2, so this shear, the 2 1/3, applies for x being between 1 and 2, so that applies to the segment from C to, D, which you can't see. Okay, so x is between 1 and 2. That means until I get to point D. Okay, and then the moment equilibrium, the sum of the moments about point O is 0. Okay, so I come up with this equation. Moment is equal to 2 1/3 x minus 5 1/3. For x being between 1 and 2, that means between points C and D. But then at D, a new equation has to kick in. Because at point D, I've got a point moment. Okay, now something that I notice here, you see the shear is 2 1/3 for x being between 1 and 2. I say until D, but at D, there's really only a point moment that kicks in. There's no new vertical reaction or force. So technically I could say till point E. This x, the x value would apply for being between 1 and, okay, where does that stop? 1 and E. Okay, so 1 and E, I meant to say 1 and 4. So at C, I'm at 1 meter. At E, I'm at 4 meters. So technically this shear would be 2 1/3 for x being between 1 and 4. But I'll rewrite the equation anyway. When I take cut DD, so that'll be the next thing, I'll take cut DD. You see it there between point capital D and capital E? Okay, so take note of these equations for the internal shear and moment between C and D. So analyzing the beam segment to the left of section DD, cut DD, I don't have to rederive what I called equation 5 from the previous slide because there's nothing new happening at D. So the shear that I calculated in equation 5 is still holding true. Now with regards to the moment, notice that at point D, a new moment jumps in. I've got a 4 kilonewton per meter moment. 4 kilonewtons per meters. That's acting in a counterclockwise direction. And so what's going to happen here, take the equilibrium about point O. So I find the equation for M, and this is a typo here. X should be between 2 and 4. Okay, so notice that at point D, X is 2, because I'm 2 feet, or 2 meters. I think this was in meters. 2 meters to the right of B. So this is the equation for internal moment, given that X is between 2 and 4. Okay, so something I notice here, if I stick in X is equal to 4, what happens if I substitute X is equal to 4? What number do I get? What number do I get? 2 1/3 times 4 minus 9 1/3. Okay, well that'd take me to point E. At point E there was a hinge. At point E there was a hinge, remember that? So the moment should be 0 at point E. So notice that X would be 4 at the point E, and the moment should be 0 at that location. So the last thing I want to do is analyze segment EF. Segment EF, I have to do an analysis for the internal shear and moment for segment, did I say EF? I meant EG. So EG is next. So I analyze section EG. Okay, so take this part out, and here it is. Okay, EGF is where I apply a 3 kilonewton load, and the E sub y and the G sub y I found previously. So I need 2 cuts here. Remember that anytime a new load or reaction comes in, it changes the shear and moment equations. So between E and F, nothing happens, so I can take a cut between E and F. And then at F, big F, I've got a 3 kilonewton load, so I have to take another cut to the right of that, section FF. So first I'm going to take cut EE. I'm going to take cut EE and analyze the equilibrium, moments, and some of the forces in the y direction. Okay, so when I make cut EE, what am I analyzing? This portion right here between my thumbs. Okay, so that's what I have here. Internal shear, internal moment. Okay, so X is measured from E, the new frame of reference. I'm measuring from point E. Okay, so I find the equilibrium in the y direction, and I find that the shear is 2 1/3 for X being between 0 and 1. At 1, if X is 1, then I've got a load that kicks in. And then moment equilibrium, the sum of the moments about point O. Internal moment M minus 2.3 times moment arm X. And I have an equation for moment. So I'm calling this equation 8. Shear is equation 8. Moment is equation 9. And now I'm going to take a cut FF and analyze this portion between my thumbs. So that'll be the next drawing. Okay, so here is the segment to the left of section FF. So FF, I cut it right here. I'm looking at the segment right here. Okay, so X is still measured from point E. So equilibrium in the y direction, I find that the shear is negative 2/3. Be careful, this is for X between 1 and 4. I made a typo here. And I don't have any ink eradicator on me. And so I just decided to cross off my error here and put 1. So be careful, X is between 1 and 4. That means between F and G, which is to the right of O. You can't see it. So the shear, internal shear, is negative 2/3 for X between 1 and 4. Let me show you this illustration. Here x is 1, over here x is 4. And notice that the reaction at G is 6/10 kilonewtons. Okay, so in magnitude it agrees with this 6/10. And then in terms of the moment, okay, I made a mistake here. Okay, and again I ran out of ink eradicators, so this is for x between 1 and 4. So the sum of the moment's about 0.0. Okay, so I get this equation here for internal moment, negative 2/3 x plus 3. Okay, now at point G, x is equal to 4, isn't it? Because I'm 4 meters to the right of E. So try sticking a 4 in here. Stick a 4 in here, and what do you get? Okay, if you're doing the arithmetic correctly, you should get the m sub g that I determined here, which is 1/3 kilonewton meters. So that probably means that my arithmetic is okay. Okay, so where am I? So I have equations 10 and 11. So I think that's it. I think I've worked my way down the entire beam. I have to summarize all these equations and make them neat and orderly so that I can draw my shear and moment diagrams. Okay, my original drawing with all the reactions, remember this? Okay, so moving on down, I split this up into a couple different segments, A, B, B, C, C, D, E, F, F, G. Okay, so this is a summary of all my equations so far. So for segment AB, that's between 0 and 3. Okay, this diagram also tells me where I start x all over again. So remember that I started x being 0 at A, and then I started again at B, and then I started again at E. Okay, so for segment AB, okay, AB, just look at these two. Okay, sorry, I'm trying to hold the camera steady. Okay, for AB, I've got the shear and moment. And then notice that at B, I got a new x that kicks in. X is 0. So for BC, I've got 3 and 4. For segment CD, x is still 0 at B, so segment C would start at x is equal to 1. It would go until x is equal to 2. At segment D, from D to E, x starts at 2, it goes to 4. DE, 2 to 4. Okay, so where am I? So I've got equations 5 and 7. And then for EF at E, I start a new x, don't I? Start a new x at E. So from E to F, okay, F is at x is equal to 1, measured from point E, so I've got equations 8 and 9, and then F and G. So from F to G, I'm starting at x is equal to 1, going to x is equal to 4. So that's what it's telling you here, from 1 to 4. Okay, so equations 10 and 11. Okay, so now I'm going to pan the whole thing. Oh. Okay, so here's the original beam structure with all the reactions. Okay, I create a diagram here that tells me where the new x's start. Okay, and then equations for shear and moment for each of these segments. So now I'm going to graph all this. Now I will graph all this to create a visual depiction. And now I want to put it all together. So here's my original beam. And here's the shear diagram that you were waiting for. Here's the shear diagram. Okay, is the lighting okay? Or maybe that's better. Okay, so notice that I put up here at the top where the new x value starts. So between A and B, I've got a shear given by the equation negative 2x plus 3. So if x is 0, that would mean I'm at point A, then stick a 0 in there, so you'd have positive 3. Shear is 3, that's up here. What happens if you stick in x is equal to 3? You see it's 3 meters between A and B, so at this location where the pencil is, that's point B, I'd have x is equal to 3. Stick a 3 in there and you'd have negative 2 times 3 plus 3. What is that, negative 3? So that gives you this value down here. You may also remember from statics that the area under the distribution diagram is equal to the change in shear. Okay, so what that means is the load distribution diagram, 2 kilonewtons per meter times 3 meters, that's 6. Okay, so the area under the loading distribution is 6. Okay, that area is a change in shear. So notice that as I go from A to B, I go from 3 to -3. So that is a change of 6, isn't it? And I should have mentioned that it's -6 because the load is pointing down. So the area under the loading distribution would be -6. And so the change in, where was I? The change in shear is -6 as I go from A to B. And then at B, from B to C, the shear is -3, stays constant. And then what happens at C? Well, it seems to jump up 5.3, 5 1/3 actually, because that's at 2 1/3. Is that consistent with my reaction? So at C, there's a vertical reaction of 5 1/3. So that's going to represent this jump that you see right here from -3 to 2 1/3. Okay, notice that the shear stays constant throughout this segment until I get to point E where there's a hinge, because between C and E there's nothing really going on in terms of the shear. Between C and E there's no new reaction coming in, so that's why it stays constant at 2 1/3. And then at point E there's a hinge. On the other side of the hinge I still have a shear of 2 1/3. But then there's a drop here. At point F it drops down from 2 1/3 to -2/3. Do you know what that drop is? Okay, go back to this. See that 3 kilonewtons that's pushing it down? So that 3 kilonewtons represents this drop here. So 2 1/3 minus 3, what is that, -2/3? So it remains at -2/3 kilonewtons until I get to point G, and then if you want to get back to point G, you can jump up 2/3 kilonewtons. Notice that the reaction at the right side is 2/3. And so I think my arithmetic is correct. How does that look? Is that okay? So that's my shear diagram. And now here's my moment diagram. Notice that I'm labeling where the new x values start. So between A and B, x is 0 at A, x is 3 meters at B. I derive the equation -x² plus 3x. That's a parabola. You can graph that in a graphing calculator. The graphing calculator will also tell you where the maximum is at 2.25. So there's a maximum point of maximum moment in there. You can also take the derivative of this, set it equal to 0 to find the maximum. Okay, then the moment goes back down to 0 at B. Does that make sense logically? Okay, it better go back down to 0. The moment better be 0 at B because there's a hinge there. Okay, then what do we have? Between B and C, I believe I derived the equation -3x. Okay, so if x is 0, remember that x is starting at 0 again at point B. So put a 0 in there and you've got moment is 0. At point C, I've got x is equal to 1, so -3 times 1 is -3. And then from C to D, I believe I derived the equation, I hope you can see this, 2 1/3 x minus 5 1/3. Is that right? So at x is equal to 1, I'll put a 1 in there, because at point C, x is 1. So put a 1 in there, so 2 1/3 minus 5 1/3, that's -3. At point D, x would be 2, so put a 2 in there. 2 1/3 times 2 minus 5 1/3. What is that, -2/3? So that's for x is equal to 2, right? Okay, at point D, there's a moment that jumps in. You see that 4 kilonewton meter that is jumping in at point D that's going, what is that, counterclockwise? So that's going to represent a jump. So notice that this is a jump, actually a drop. So a drop from -2/3 down to -4 2/3. So there's a drop of 4 here, goes down -4 until I get to -4 6/10. Then this new equation, m is equal to 2 1/3 x minus 9 1/3. So the value of x here would be x is equal to 2, right? Okay, so I shouldn't mess up my nice drawing, but here I've got x is equal to 2, because I'm 2 meters to the right of point B where this is referenced from. Stick a 2 in there and verify that you get -4 2/3. And then at point E as an echo, the value of x would be 4. Okay, so x is equal to 4 at this location. So stick a 4 in here and verify that you get 0. Now it should be 0 because at E, remember there was a hinge. Can't be any moment there. Okay, so that seems to make sense. So there's a hinge at E, therefore no moment, and a new equation kicks in. Okay, the equation m is equal to 2 1/3 x, where x is measured from point E. So at point E, x is 0. Okay, so it makes sense that m is 0. At point F, x is 1. So put a 1 in there, and you got this 2 1/3 that you see right there. How's that? And then I've got at point F, this new equation kicks in, negative 2/3 x plus 3. So at this location, what is this? X is equal to 1, measured from point E. Stick a 1 in there and verify that you do get 2 1/3. And then over here, x is equal to, what is that, 4? I'm 4 meters to the right of point Echo. So stick a 4 in there. Negative 2/3 times 4 plus 3, is that 1/3? 0.3 with a line above it. That seems to be consistent with what my reaction at G was, my moment reaction. See that? 1/3. So that's what I see here. So how does this look? Everything seems to be good. Now there are some relationships between shear and moment. If you remember from statics, typo here, pay no attention to that. I said a minute ago that the area under the distribution diagram is equal to the change in shear. I already told you about that. Rewind the film if you don't remember that. What else did I say? Well, let's deal with this. The derivative of m with respect to x is v. In layman's terms, I could say the slope of the moment diagram is equal to the shear. Okay, what does that mean? So, for example, let me pick something easy here that I don't actually have to differentiate. Like, for example, between B and C, the slope is negative 3, isn't it? Okay, go back to the shear diagram. Isn't that the value of shear, negative 3? Okay, so that makes sense. Okay, now what about between C and D? The slope is 2 1/3. Okay, was that the value of the shear between C and D? Okay, it was. In fact, the value of shear between D and E, and between E and F, was also 2 1/3. So that seems to be the slopes that I see here. And then between points F and G, the slope is negative 2/3, negative 0.6, where the 6 repeats. And I notice that that's the value of the shear between F and G. Okay, if I went too fast, pause the video and go back and retrace my steps. Okay, so what did I just tell you? What was that? I said that the slope of the moment diagram is equal to the shear. So how's that? And one more thing while I'm at it, I'll keep this simple. What's the value of the slope at the top of this parabolic? Well, if you remember from my first semester calculus class, the slope up there is 0, isn't it? Okay, so if the slope of the moment is equal to shear, then the shear at this midpoint value between A and B should be 0, which it is. How's that? Okay, and I might as well take it one step further. What is the derivative of negative x squared plus 3x? Derivative would be negative 2x plus 3. Okay, negative 2x, the slope, negative 2. Okay, so negative 2, does that sound familiar? Slope of the shear, negative 2. Okay, go back and take it slower if you didn't catch that. Okay, so what did I just tell you? The slope of moment is equal to shear. And then while I'm at it, what else do I have here? The integral of shear is equal to the change in moment. The area under the shear curve is equal to the change in the moment. The area under the shear curve is the change in moment. So, for example, okay, between A and B, positive area, negative area, they're the same magnitudes. They cancel each other out, meaning that between A and B, there should be a net change in moment of 0, which there is. Starts off at 0, ends at 0. Okay, so that makes sense. Okay, so area under the shear is change in moment. Okay, between B and C, what's the area of this rectangle? This one right here. What is that? Negative 3, isn't it? See, this value down here is negative 3. It's got a width of 1. So the rectangle between B and C has an area of negative 3. Okay, what does that area represent again? Change in moment. So between B and C, there's a change in moment of negative 3. Okay, so that seems to make sense. Between C and D, what's the area of this rectangle? 2 1/3, isn't it? What is that, 2 1/3? So between C and D, I'm expecting a change in moment. a change in moment of 2 1/3. Okay, between between C and D, what's the change between -3 and -2 1/3? Okay, is that in fact 2 1/3? Did I say that right? So at C, the moment is -3. At D, it's -2 1/3. -3 plus 2 1/3 is -2 1/3, isn't it? How does that look? Okay, at D, there's a moment that jumps in that makes this drop down to -4 2 1/3. So between D and E, what's the area under the shear? Talking about this rectangle here. 2 1/3 times 2, what is that? What is that? 4 2 1/3. Okay, so what is the change in moment between D and E? Change in moment. -4 2 1/3 to 0. So that's a change of 4 2 1/3. Positive 4 2 1/3, which is the area of this rectangle. How does that look? From E to F, area of 2 1/3. 2 1/3, 1 times 1 is the width, height is 2 1/3, positive 2 1/3. So between E and F, change in moment from 0 to 2 1/3, that is 2 1/3, makes sense. The area under the shear diagram from F to G is -2 1/3. So is that the change in moment? Okay, so change in moment. I go from 2 1/3 down to 1/3. So what is that? Did I say this right? Let me try that again. The area under the shear curve between F and G is 3 times 2 1/3. 3 times 2 1/3, that's 2, isn't it? This area is to -2. Okay. I think I got confused there a minute ago. So that area is -2, right? Okay, so -2 is the change in moment. Okay. So it goes from 2 1/3 to 1/3. Yep, that's a change of -2. Yeah, I said it correctly that time. Okay, so that's a demonstration of these relationships. How was that? So to finish this up, what can you tell me about deflected shape? When I put loads on a beam, it will deflect ever so slightly. It'll deflect just a little bit. Well, deflected shape, in terms of the deflected shape of this, it tends to be concave in the direction of the moment. So for example, between A and B, it tends to be concave up. So it's concave in the direction of the moment, positive. Okay, here it's concave down between B and C, and between C and D it tends to be concave down. Tends to be concave down between D and E. That's this little red arc you see that I drew. Between E and F tends to be concave up. Between F and G it tends to be concave up. One more thing I want to mention. What is an inflection point? An inflection point would be where there is 0 moment and a change in concavity. So I wouldn't consider B to be an inflection point because there's a hinge there. Similarly with E. But for example, if this parabolic curve were to cross the horizontal axis represents the beam, wherever the moment equation crosses the beam, that would be a location of 0 moment. In other words, an inflection point.